Part 3. The Alien Legacy. We looked for signals from the stars, but instead, we found a stone. 3I. Atlas is a physical piece of a world that might not even exist anymore. As it prepares to leave our system and vanish into the eternal dark, we realize we aren't just observing a comet. We are looking at a fingerprint of the galaxy itself. This is what it means to be part of the interstellar exchange. What interstellar objects reveal about other star systems? Only a very small number of objects have ever been observed entering the solar system on trajectories that cannot be traced back to its own gravitational reservoir, arriving instead from interstellar space with velocities and paths that indicate formation elsewhere and no prior connection to the Sun. They are not hypothetical constructs, not statistical expectations derived from models, but physical bodies whose presence is registered directly through light, motion, and interaction with solar radiation, carrying material that condensed around other stars under conditions that can no longer be observed in place. For most of their existence, sometimes spanning millions or even billions of years, such objects drift through the galaxy unnoticed, bound to no star, shaped only by the environment of interstellar space, until a chance alignment brings them through a planetary system not their own. When one of these objects enters the solar system, it does not announce its origin explicitly, nor does it arrive with contextual information about the environment in which it formed, and yet its physical properties reflect that history in subtle ways that can be measured, compared, and interpreted with caution. Its trajectory preserves information about its motion through the galaxy. Its composition reflects the chemistry of another protoplanetary disk, and its response to solar heating reveals how material assembled elsewhere behaves when exposed to conditions it has never encountered before. In this sense, each interstellar object functions not as a message, but as a fragment, offering partial access to processes that normally remain beyond observational reach. Unlike planets or stars, which are observed primarily within their native systems, interstellar objects provide direct samples of material displaced from its place of origin, allowing astrophysical theories about planetary system formation to be tested against physical evidence rather than inferred solely from distant observation. They do not represent entire systems, nor do they preserve complete histories, but they constrain what those systems could have been like, ruling out some possibilities while leaving others open. This constraint arises not from what the object is said to mean, but from what it does under observation. The ability to extract such information from a single object rests on a methodological shift that is common in astrophysics, where direct access to environments is rare and knowledge is built instead through indirect reconstruction, using limited data to infer broader conditions. In this approach, an object is not treated as an isolated curiosity, but as a physical outcome of processes that operate repeatedly across many systems, even if only a few outcomes ever intersect with observation. The question is therefore not whether one object is representative, but which aspects of its behavior are consistent with known physical mechanisms and which suggest variation. Planetary systems form within rotating disks of gas and dust surrounding young stars, where material interacts through gravity, collision, and gradual accretion, producing planets, smaller bodies, and a wide range of transient structures as the system evolves. During these early stages, interactions are often chaotic rather than orderly, with bodies migrating, colliding, and scattering as mass is redistributed and orbits are reshaped. In such an environment, not all material remains bound to the system that formed it. Gravitational encounters between small bodies and growing planets can transfer energy efficiently, altering trajectories and in some cases accelerating objects beyond escape velocity, removing them permanently from the system in which they originated. These ejection processes do not require rare or exceptional conditions, but arise naturally as a consequence of planetary growth and migration, particularly in systems that contain massive planets capable of strong gravitational influence. Over time, this leads to a steady loss of material, with countless small bodies expelled into interstellar space. From this perspective, interstellar objects are not anomalies, but the residual products of a common process, sampled only when their paths happen to intersect with a system capable of detecting them. Their rarity in observation reflects limitations of detection rather than scarcity of formation, and each detection therefore represents a small but meaningful intersection between theory and evidence. What matters is not how many have been seen, but what can be learned from those that have. Because these objects are expelled during phases of planetary system evolution that are otherwise difficult to observe directly, their existence provides indirect access to the dynamical history of systems beyond the solar system, revealing not what those systems look like today, but how they behaved when planets were still forming and orbits were still unstable. The conditions required to eject material efficiently imply the presence of massive bodies, prolonged gravitational interaction, and periods of dynamical rearrangement, all of which leave imprints on the small bodies that are scattered outward and eventually detached from their parent stars. In this way, interstellar objects preserve a record not of equilibrium, but of disturbance. The structure of a planetary system during its early evolution is shaped by competition between accretion and loss, as material simultaneously coalesces into larger bodies while other fragments are displaced, redirected, or expelled, depending on the balance of forces acting within the disk. Gas drag, resonant interactions, and close encounters with growing planets all contribute to this redistribution, creating pathways by which material can migrate inward, collide, or be accelerated outward beyond the gravitational reach of the star. These processes do not operate in isolation, but overlap in time, producing outcomes that vary from system to system while remaining governed by the same physical principles. When an object is expelled into interstellar space, it enters an environment that differs profoundly from the one in which it formed, where radiation fields are weaker, temperatures are lower, and interactions are rare, allowing its physical state to remain largely unchanged for extended periods. Over millions or billions of years, such objects travel through the galaxy without significant alteration, preserving within their composition and structure the conditions of their origin, not as a snapshot, but as a constrained range of possibilities. This long isolation is what allows interstellar objects to function as physical archives, even though those archives are incomplete and fragmented. Chemical composition provides one of the few accessible links to this origin, because the relative abundances of volatile and refractory materials reflect the temperature, pressure, and radiation environment of the protoplanetary disk in which the object condensed. Differences in these environments can lead to measurable variation in composition, even among objects that otherwise behave similarly under solar heating, allowing comparison between interstellar objects and bodies formed within the solar system to proceed through chemistry rather than morphology alone. Such comparisons do not require exact matches, but depend on identifying deviations that cannot be easily reconciled with local formation conditions. At the same time, interpretation is constrained by observational limits, because only the most abundant components can be detected reliably at the distances and brightness levels typical of interstellar visitors, leaving much of the chemical inventory inaccessible. This limitation does not negate the value of the data, but it narrows the scope of inference, ensuring that conclusions remain provisional and grounded in what can be measured rather than extrapolated beyond the evidence. In this respect, uncertainty is not a weakness, but an integral part of the observational process. The solar system itself provides a necessary point of reference, not because it represents a standard against which all others must be judged, but because it is the only system whose small body population can be studied in detail across a wide range of conditions. Comparisons between interstellar objects and solar system comets therefore illuminate both similarity and difference, revealing which properties are shared across systems and which may be contingent on local formation history. These comparisons gain meaning not through direct equivalence, but through contrast. When similarities are observed, they suggest that certain processes of planetary system formation may be common, producing comparable outcomes despite variation in stellar environment. When differences emerge, they indicate that alternative pathways exist, shaped by factors such as disk composition, stellar radiation, or the timing and extent of planetary migration. Interstellar objects occupy the intersection of these possibilities, sampling outcomes without revealing the full range from which they are drawn. I will continue from here, moving deeper into formation mechanisms, chemistry, and the limits of small number statistics, while maintaining this same observational flow. As attention turns from individual detections to the environments that produce them, it becomes clear that interstellar objects do not emerge from stable, mature systems, but from phases marked by rearrangement, where gravitational interactions redistribute material before long-term equilibrium is established. During these stages, growing planets exchange angular momentum with surrounding debris, resonances shift, orbits cross, and small bodies are repeatedly scattered, sometimes inward toward the star and sometimes outward along trajectories that no longer remain bound. In such conditions, ejection is not an exceptional outcome, but one of several natural pathways available to material that fails to settle into a long-lived orbit. The efficiency of this process depends on the architecture of the system, particularly on the presence and migration of massive planets whose gravitational reach extends far beyond their immediate vicinity, altering the fate of countless smaller bodies through repeated encounters. Where migration is extensive, scattering becomes more effective, increasing the probability that material will be accelerated beyond escape velocity and removed permanently from a system, while in more dynamically quiet environments, small bodies may remain bound for much longer periods. These differences imply that the population of interstellar objects reflects not a single formation pathway, but a range of system histories sampled unevenly by chance encounters with observation. Once expelled, an object enters interstellar space with properties fixed by its final interaction, carrying away information about the disk from which it originated, the planets it encountered, and the timing of those encounters relative to its internal evolution. Over long intervals, external influences are minimal, allowing structure and composition to remain largely unchanged, and preserving a record that is neither pristine nor random, but constrained by the processes that led to its ejection. This persistence is what allows interstellar objects to function as physical traces of distant systems, even though their histories cannot be reconstructed in full. When such an object later encounters the solar system, its behavior under solar heating provides an additional layer of information, because the way it responds to energy input reflects both its composition and its internal structure, revealing similarities and differences relative to bodies formed locally. Moderate activity, delayed onset of sublimation, or unusual relative abundances of volatile materials can each point to formation conditions that diverge from those typical of the solar system, even if no single measurement is decisive on its own. Interpretation, therefore, proceeds through accumulation rather than confirmation, with each observation narrowing the range of plausible origins. At this stage, the small number of observed interstellar objects becomes a defining constraint, because conclusions drawn from a handful of cases must remain provisional, sensitive to selection effects and detection bias rather than treated as representative of a broader population. Astrophysical inference often advances under such conditions, not by claiming generality, but by identifying which models remain consistent with the data and which can be excluded, even when the dataset is limited. In this framework, uncertainty is not eliminated, but structured. Future survey instruments are expected to alter this balance, increasing detection rates and expanding the range of observed behaviors, not by changing the nature of interstellar objects, but by intersecting their trajectories more frequently and earlier in their passage. As detections become less rare, individual cases will shift from being singular reference points to components of a developing population, allowing statistical trends to emerge where only qualitative comparison was previously possible. This transition will not remove uncertainty, but it will redistribute it, moving interpretation from isolated examples toward comparative context. 3i Atlas occupies a transitional position within this evolving landscape, arriving at a time when interstellar objects are still rare enough to command individual attention, yet observed with instruments capable of placing its behavior alongside that of many solar system comets. Its contribution lies not in resolving questions definitively, but in extending the empirical basis upon which those questions are framed, linking local physical processes to material formed elsewhere and reinforcing the idea that planetary systems exchange material with their surroundings more readily than once assumed. In this sense, interstellar objects do not conclude an investigation, but open it outward, shifting focus from what is observed locally to what must be occurring elsewhere, across systems that cannot be studied directly but nonetheless leave traces that occasionally cross our field of view. The story they tell is incomplete, fragmentary, and constrained, yet it is grounded in physical presence rather than inference alone, making each encounter an opportunity to test ideas about planetary system formation against tangible evidence. As detection rates increase and observation windows widen, the character of interstellar object studies begins to shift, not toward certainty, but toward context, where individual trajectories and compositions can be placed alongside others observed under comparable conditions. This change does not depend on any single instrument, but on the accumulation of coverage over time, as repeated surveys intersect a growing fraction of passing objects earlier in their approach, allowing behavior to be tracked across longer intervals rather than inferred from brief encounters. With earlier detection comes the possibility of observing the onset of activity, the gradual response to heating, and the sequence by which structure adapts or fails, adding temporal depth to what has so far been a largely episodic record. Even as this broader context develops, the fundamental limitation of indirect inference remains, because interstellar objects arrive without labels and depart without explanation, leaving interpretation to proceed through comparison rather than confirmation. Models of planetary system formation can be constrained by their compatibility with observed behavior, but they cannot be uniquely identified, and multiple histories may remain consistent with the same set of measurements. In this environment, progress is measured not by definitive answers, but by the gradual narrowing of plausible scenarios. Within this narrowing, 3i Atlas contributes by occupying a region of parameter space that had not previously been sampled, combining interstellar origin with cometary activity that is neither extreme nor absent, and doing so at a time when comparative data from solar system comets is extensive. Its behavior under solar heating, its chemical signatures, and its structural response do not stand alone, but gain meaning through their relationship to patterns already observed locally, even as they extend those patterns beyond the solar system. What it adds is not resolution, but continuity, linking rare interstellar encounters to familiar physical processes. As the scale of consideration expands from individual objects to planetary systems, and then to the galactic environment in which those systems form, interstellar objects occupy a unique position, bridging observational domains that are otherwise separated by distance and time. They connect the physics of small bodies to the dynamics of planetary formation, and local measurement to distant process, allowing ideas developed in one context to be tested, cautiously, in another. This connection does not close questions, but it reframes them. The picture that emerges is one in which planetary systems are not closed architectures, but permeable structures that exchange material with their surroundings, losing fragments during periods of instability and contributing to a population of objects that wander between stars. Interstellar space, in this view, is not empty, but populated sparsely by remnants of formation processes repeated across the galaxy, most of which will never be observed, and some of which will pass unnoticed even when they do. Occasionally, one of these fragments enters a system capable of detecting it, and for a brief interval its presence becomes measurable, its behavior recorded, and its properties compared against expectation. These moments do not offer complete histories, but they provide constraints that did not exist before, grounding speculation in physical interaction rather than abstract possibility. In this way, each detection contributes incrementally to an understanding that grows not through accumulation of certainty, but through disciplined attention to what can and cannot be inferred. As this trilogy concludes, the emphasis rests not on answers delivered, but on perspective gained, where local observation and distant formation are understood as parts of a continuous process rather than separate domains. Interstellar objects mark the points at which that continuity becomes visible, crossing from one system to another and briefly illuminating the processes that shape worlds far beyond direct observation.